I believe I gave you the formula for ammonium nitrate, so you should have that to help you find the molar mass of ammonium nitrate. Yes. The question is, when you're doing the significant figures at the end, do you use the mass that you find off the periodic table? And yes, rounded to the nearest hundredth. So make sure that you rounded it right, and then that will count. So usually 4 or 5 significant figures for the molar mass. Yes, 6.02. No, that's not exact. So that counts for 3 significant digits. So what's your next step? 454 grams in 1 pound. Pounds cancel. Then what? Good. 1 mole over 80.06 grams. Grams cancel, and that's moles of ammonium nitrate, but you want formula units. So how many formula units are in 1 mole? So 6.02 times 10 to the 23rd. Formula units in 1 mole. Moles cancel. Run your numbers, and you should get formula units. Good job. 1.71 times 10 to the 26th. Formula units. Yes or no? Making sense? Go ahead. You have to have the mass of ammonium nitrate because that is the only way to get you into moles from mass of the compound. So anytime, and this goes back to the page before this, when converting to or from moles to atoms, molecules, formula units, that's when you use the 6.02 times 10 to the 23rd. But anytime it deals with moles and mass, that's when you have to use the mass that you find off the periodic table. Okay? The question, it didn't directly say how many grams or how many moles, but to get to formula units, the only thing you know about with formula units is moles. Formula units in a mole. And then the only thing else you know about moles is grams. Does that kind of lead the thinking? Okay. Other questions on this? All right, while I am thinking about it, let me show you something on Blackboard. On Blackboard, under Extra Practice Worksheets, there is a practice mole homework. That is just like the page. It's not the same problems, but it's similar to what we've just done. This is the answer key for that. Notice on this particular homework, I was using a different test, or a different textbook rather, and that textbook used 6.022, I think, or it maybe even used 6.023. So just note that it's 6.02 for you guys and make your answer accordingly if it makes a difference. The process is still going to be exactly the same. Also, there are a few of the question answers on this particular worksheet that do not use significant figures. We do. Why do I leave that on there if it's not exactly like what we do? Because these are my questions. And I think you might realize my questions tend to be not just the super simple questions. We go either start off with some dimensional analysis or have to do more dimensional analysis at the end, which you need to be able to do. So make sure that you look at these. This is really, really good practice in addition to the sapling homework. While I'm here, I want to point out the stoichiometry, which is what we're going to start on next. There is also a practice stoichiometry homework and an answer key. Again, there is a small problem. Here it tells you about it, so just make note of that when you print it out. Just fix that little spot right there that you're going to see on that question, which is problem 3. One more thing that's here that you need to print out before Monday. So this is really important. Do you see where it says test 3 practice problems? Print that out before Monday. I don't know that we will get to it on Monday, but I know for sure on Wednesday we will. So print out, if you haven't already, print out the test 3 practice problems. There is an answer key already there, but we are going to work through some of those in class next week. So make sure that you print this out and add it to your notes. Lastly, next week's notes are over gas laws. On Blackboard, under the extra practice videos, not the lecture videos, which is what Travis is doing now, but under the extra practice videos, there is a gas law video and worksheet. And that is different than the notes that I'm giving you. It's the same material, but it's more practice. Now, why am I giving you all of this now and maybe earlier I didn't have this much? Well, there were a lot of nomenclature practice online, so there's still a lot of stuff online extra to help you. Now, though, after some of you have had 2 exams, you're ready to really listen and work a little harder. Some of you. So, I know a lot of people aren't here today, but I'm going to say this anyway, and you guys get the benefit of this comment. And again, I will say if the shoe fits, wear it. That means if this is your situation, then apply this to you. On the first day of class and on the syllabus, which we didn't have the first day of class, but on the syllabus, and I talked about this, I think, in the video, I told you how to pass this class. I'm going to repeat that for you again because I think some of you need to be reminded of what can I do to pass, okay? Monday was the first day of new material. Now, obviously, we're on Wednesday. Ideally, your scenario would have been on Monday. Monday night, after your class, you went home and you looked over the work that we did. You did a few practice problems, and it looks like a lot of you did do that ammonium nitrate problem, so that's great. So you do the few problems, start on the sapling homework. Yesterday, do a few more sapling problems, 2 or 3. Look over the notes. I'm talking maximum 30 minutes, more like probably 20 minutes of actual study time. Tonight, when you get home as soon as you can, read over tonight's notes. Do a few problems, do a few sapling problems, read over Monday's notes. Tomorrow, do the same thing. Now, I know it's fall break. Some of you are done for 4 or 5 days and you're not going to think about it. And that's wonderful for you if you can do that. For those of you that are saying, you know what, forget fall break, I need to pass chemistry, then try this. Go online, print out those mole worksheets, print out the stoichiometry worksheets. Get those done within the next few days. Then if you really want to be proactive and really ace that test, go on and go watch the gas law video. Then next week when we come back and Dakota has passed and we're here on Monday night and we're here again on Wednesday, then you guys that have done all that extra, you're going to be like, I got it. Man, this is making sense to me. Or those few questions you don't know the answer to, you can either ask me or you can ask Dakota. Then by the time the next Monday comes, which is when our next test is, you got it under control. No problems at all because you have consistently studied. The night before when everybody else is cramming, you're just going to be in bed and getting a good night's sleep and it'll be great because you have studied every night. I promise you this method works. Now some of you just refuse You say, I don't have time to do that. That's your choice. But it takes less time to do that every day than it does to cram for 3 or 4 hours before a test. You can try it. I've had students that try it and they come back and they're like, yeah, that really works. And so it's your choice. But I do think it's something you need to consider if you're struggling right now. All right, so the new topic for tonight is stoichiometry. Actually, I have 2 new topics, stoichiometry, and we have oxidation reduction. So let's look at stoichiometry. The hardest part about stoichiometry is saying the word and spelling it. It's not as hard as the word makes it look like it is. What is it? Let me explain it to you from a kitchen standpoint, okay? Let me explain it for you in that manner first. Let's say that I want to make some boxed brownies, and I use that example because almost everybody has made boxed brownies sometime in their life. So let's say that we're going to make a boxed brownie mix, and so you have your box of brownie mix. Now, I haven't made this lately, but you all can tell me if I'm got it close. Is it like 1/3 of a cup of oil? Is it 1 egg? 2 eggs and 2 tablespoons water or something like that? So it's basically the brownie mix, 2 eggs, oil, and water. So somebody, some chemist, some food chemist, wouldn't that be a nice job? A food chemist? Some food chemist somewhere figured out the amount of baking soda or baking powder, flour, cocoa, sugar that they put in this powder that would go perfectly with the 1/3 of a cup oil, the 2 tablespoons water, and the 2 eggs to make that perfect brownie that we all love. Now, you can leave out the oil and just make no fat brownies. You can add the applesauce. But somebody somewhere, probably lots of somebody somewhere, did lots of taste tests, and everybody agreed, or the majority agreed, this is how we really, really like it. And that's the recipe then that's on the back of the box, and that's what we say, this is how you make these brownies. The stoichiometry of that is the quantity of reactants that will produce the quantity of product. So the reactants are the brownie mix, 2 eggs, 1/3 cup of oil, and 2 tablespoons water. We'll make a little 9x9 pan of brownies that are the specifications that they might say, the 2 inches thick or 2, whatever those, they're the perfect scenario. And I'm not saying you couldn't make them flat or whatever. Now, you say, look, I only have half of that amount of oil. Will my brownies be exactly perfect if I use all the other ingredients the same and use only that half amount of oil? No. What would you need to do, and I'm not going to say how to do it because that gets in another concept there, but what would you do in general to make that perfect still? Have everything else. That whole thing that you just did is stoichiometry. Except instead of cooking, we're applying it to a balanced equation. For instance, 2 somethings of sodium, might be 2 grams of sodium, reacting with whatever amount of chlorine to make 2 pounds of sodium chloride. Or I might want to know how much chlorine is it going to take to react with 2 grams of sodium. All of that can be determined with a balanced equation and knowing how to use it. So the whole process is called stoichiometry, and it's called the quantitative relationship among products and reactants in a balanced equation. First, I want you to know, without the law of conservation of mass, this could never happen. That had to be true. The law of conservation of mass is true, so without that, this won't work. But we know it's true, so we're going to say, yes, it works. The other thing that's different in what we're doing now compared to what we just did in the last problem is we have to do mole-to-mole ratios, and I'm going to explain those in just a moment, but just keep that term in mind, mole-to-mole ratios. So let me explain all of this page, and then we'll actually do the problems. All of this is more of an explanation of letting you understand the whole concept, and then this is the true math down here. Looking at the balanced equation, one way to look at that is from an atom point of view. Could I say that this is 2 atoms of sodium? Could I say that? What would I call this then? One what? 1 molecule of chlorine. Why is it called a molecule? Because it's diatomic. Good. And what's the smallest particle of sodium chloride called? Formula unit. So what is this? 2 formula units of sodium chloride. So 2 atoms of sodium react with 1 molecule of chlorine to produce 2 formula units of sodium chloride. Does that make sense? You don't have to write this down, but just does that make sense? Now, can I ask you to go to the lab and bring me back 2 formula units of sodium chloride? No. Why? Why can't you bring me back 2 formula units of sodium chloride and put them in my hand? Think about formula units. Or read the page. It tells you. What's it say? They're too small. Can you bring me 2 atoms of sodium? Can you see 2 atoms of sodium? Could you see 2 formula units of sodium chloride? No. And some of you are like, I don't know if you could or not. Well, you all should see yourself. You're acting like the 8 o'clock class today. I mean, you're like, there's like 6 people like that right now. Okay, so here, I'll try to be more entertaining. Let me ask you a question. How many atoms are in a mole? 6.02 times 10 to the 23rd. Have you written that number out? Have you put 6.02 but then put just 602 and then 21 zeros? Is that a big number? Yes. That many atoms is in a mole. That many formula units is in a mole. So are you going to recognize 2 formula units or 2 atoms? You going to be able to fill those if I just throw them at you? No. No, they're too small. You can't. So that's not a good way to look at this. That's fine to balance it that way, but that's not a good way to look at it when you're trying to do math with it. A better way is to look at the molar relationship. So one thing that we will do is look at that molar relationship. So what is this? 2 moles of sodium react with 1 mole of diatomic chlorine to produce what? 2 moles of sodium chloride. Now, do I know anything about moles that I can go to the lab and measure? Grams, which is why we have this information down here. Look at your periodic table. What is 22.99 grams per mole? Is that the mass of sodium? So 2 moles of sodium, with each having a mass of 22.99 grams per mole, does that mean the total amount of sodium is 45.98 grams? Can you do that in your head? Make that 23 times 2 is 46, and then you got it? 45.98. Does that make sense? Okay. 1 mole of chlorine, because it's diatomic, is 70.90 grams. Now, why am I saying it's 70.90 grams? Because it's 35.45 times 2, yes? Now, add up 45.98 and 70.90. You get 116.88, don't you? All right. What have I said? Let me show you again what I've said. I have said 2 moles of sodium react with 1 mole of chlorine. So I have said 45.98 grams of sodium reacts with 70.90 grams of chlorine, and that total mass, you told me, was 116.88 grams, right? If the law of conservation of mass holds true, then the 2 moles of sodium chloride should also have a mass of 116.88 grams. What is 1 mole? Look back at your previous, two pages previous in your notes. Do you see the picture where we had the moles of sodium chloride? What does it say the mass is? 58.44 grams. So 2 moles is 2 times 58.44, which is 116.88 grams. Now, what does that mean? That means if I'm cooking sodium chloride, if I have a recipe to cook sodium chloride, then my recipe would say take 45.98 grams of sodium, mix it with 70.90 grams of chlorine, and you will get out 116.88 grams of sodium chloride. Do you see that? And if I wanted to double the recipe, I'd just double the reactants, right? If I wanted half that amount of sodium chloride, I would just have the reactants. Yes? Does that make sense? The simplicity of that? But here's the problem. Most of your chemistry equations are not like cooking where you want to halve it or double it or triple it. You might want 2 tons of sodium chloride, or you might want 2 grams of sodium chloride, or maybe you only have 1 gram of chlorine to use. You want to know how much sodium you're going to need to react with that. So that's where the process of stoichiometry comes in. I wanted to explain all this to get you to understand the concept of how the law of conservation of mass works with the actual numbers, but now we're going to do stoichiometry. The difference in stoichiometry and what we just did on the previous page is that we change from one substance to another. Look at the previous question that you did. It said, how many formula units are in 50 pounds of ammonium nitrate fertilizer? The whole problem was talking about what? Ammonium nitrate. Now look at this problem. How many moles of chlorine are needed to react with sodium? So we have 2 different substances. What we have to do because of the 2 different substances is we have to have a balanced equation, and from the balanced equation we use what is called that mole-to-mole ratios that I told you about earlier. Where do the mole-to-mole ratios come from? They come from the coefficients, and that's what this statement is. 2 moles of sodium react with 1 mole of chlorine to form 2 moles of sodium chloride. So any of these coefficients can be mole-to-mole ratios with each other. So 2 moles of sodium equals 1 mole of chlorine. 1 mole of chlorine equals 2 moles of sodium chloride. 2 moles of sodium chloride equals 2 moles of sodium. Do you see that? So that is the magic step of stoichiometry that gets us from one substance to a different substance. So let's try this problem, and then I'm going to give you a little more details to help you understand it. What's our given? And we have to put who it is. So 31 grams of Na. You have to put who you're dealing with. So 31 grams of sodium. You have to get to moles of chlorine, but in order to get to moles of chlorine, you have to know moles of sodium. So how do you get sodium to chlorine? What is it? What's the mass of sodium? So where does 22.99 grams go? So 22.99 grams goes on bottom. What goes on top? 1 mole. If you'll pick up your pencil, you'll stay awake easier. Won't you try it? Well, like, use it. So 31 grams of sodium 22.99 grams are in 1 mole, so that leaves moles of sodium on top. But I don't want moles of sodium. Who do I want? Moles of chlorine. So this is where I use what's called the mole to mole ratio. So where do I get the mole to mole ratio from? Balanced equation. So I go find my balanced equation, and I tell you what I'll do. I'll write it here because I think you probably can't see it with the way I have it. So 2Na plus Cl2 yields 2NaCl. The number of moles of sodium goes on bottom. What goes on bottom? 2 moles of Na. What goes on top then? 1 mole of Cl2. Run your numbers and tell me what you get using proper significant digits. What do you get? 0.674 moles Cl2. Yes or no? Okay. Now then, let me tell you what students don't like about this. This is not the problem. This is not the problem. Because isn't that what we just did Monday? That's exactly what we did Monday. The problem is this conversion factor. This conversion factor confuses people because we have said that the conversion factor, or a conversion factor, is a number and its unit that equals another number and a different unit. So you understand if I say 12 inches equals 1 foot, you agree 12 inches is the same as 1 foot. That makes sense to us. 3 feet is the same as 1 yard. That makes sense to us. But here I'm telling you 1 mole of chlorine is showing up as if it's equal to 2 moles of sodium. And so you're saying, but that's not true. Is anybody saying that? Anybody thinking that at all? Y'all are just too sleepy. So you're thinking, wait a minute, 1 mole of chlorine is not the same as 2 moles of sodium. So how can I put that there? Because that really isn't the same. All right, I'll show you. How many people are here? I can't hear you. How do you know? Forget the fact that you saw me walk back here. You see what? 2 feet. That's it. Whoever said that is exactly what I'm talking about. That is exactly what I'm talking about. What did she say? 2 feet equals, does that make sense? So if you had seen 4 legs back there, you would have said 4 legs equals 2 people. Does that make sense? That's how you can use that mole to mole ratio. Because it's a ratio. No, 2 legs do not mean exactly the same thing as 1 person. If you took the weight of 2 legs versus 1 person, there's difference. But we're not talking about the weight. The weight gets taken care of in the molar mass. We are saying the ratio, it's 2 legs to 1 body, 10 toes to 10 fingers, 10 toes to 1 nose. Do you see what I'm saying? That's how this works. That is the same concept of how that works. Does that make sense? All right. Let's go to the next one then. What's our given? If you guys will talk to me, we will get done faster. All right, so be with me. What's the given? So 0.50 moles of chlorine. This time you are in moles already. So what is your next step now? Mole to mole ratio. Now you're ready for the mole to mole ratio. If you're in moles, then you don't need to go to grams. You're ready for the mole to mole ratio. So how many moles of chlorine are in our balanced equation? 1. So it's 1 mole of Cl2 on bottom. What goes on top? 2 moles of Na. Now what does the question ask for? So are we done? Yes, and do not pick up a calculator. What's the answer? 1. So 1.0 moles of Na. Now, something that I would do if I were you, especially those of you that are kind of struggling right now with this maybe, go back to this problem and give yourself some notes. This is the given. And substance. You have to tell the substance this time. This is the mass, and then this is the mole to mole ratio. Also, make yourself a little note over here on the side. Mole to mole, mole to mole ratio converts one substance to another. That is huge. Without a mole to mole ratio, you cannot have stoichiometry. Hold on one second. Also, the mole to mole ratio comes from balanced equation, which should also tell you you have to have a balanced equation. So mole to mole ratio converts one substance to another, and the mole to mole ratio comes from the balanced equation. Now, your questions.
It's not always going to be going from like sodium to chloride, chloride to sodium. So like if they ask for something else, we're going to have to like know like the balanced equation for it all.
You will have a balanced equation given for you.
Okay.
I will give you the balanced equation to do this. You have to have the balanced equation.
I didn't know if you were going to make us remember like if like, you gave us like, a problem and like.
You would no. You would never have to know every equation. No way. Yeah. No. We're going to do more of these. We're going to do more examples. This is just showing you one example. Okay. All right, let's do the next problem. I just used sodium chloride because we've talked about sodium chloride a lot already, and so I just used this for my example. So let's look at the last one on this page, and it says, how many pounds of sodium are needed to produce 2 tons of sodium chloride? Guys, I purposely gave you some simple ones, and then I just threw whammy on you. But that shouldn't be hard, because what am I dealing with when I'm talking about tons? What's your thought? What's going on in your brain? So tons to grams, and then, oh yeah, grams to moles, mole to mole ratio, then back to wherever I need to go. Does that make sense? So all I'm doing at this point is throwing in regular dimensional analysis in front of stoichiometry, and then at the end again, dimensional analysis. So do it. Try it. Right now. How many pounds are in a ton? Okay. So 2 tons of NaCl. What goes on top? So 2,000 pounds in 1 ton. This is still NaCl. Now what do I do? So what goes on top? And that's still NaCl. What am I ready for now? So how many grams are in a mole of NaCl? That's great. That's right. So where does 58.44 grams go? 1 mole on top. And now what are we ready for? Mole to mole ratio. So what am I trying to find? So what goes on top? No, what goes on top is what you're trying to find. So what goes on top? 2 moles of Na. Now where am I getting the balanced equation? It's up here. I'd already written it down. All these problems refer to the same balanced equation. So 2 moles of Na on top. We have to get out of sodium chloride. What is it? Also 2 moles of NaCl. That gets me out of sodium chloride. Now I'm in sodium, but I don't want moles of sodium. I want, so I go moles of sodium 2, and then grams 2. So do it. And then my last step is what? Good. And that's still Na. If you wanted to not put as many things in your calculator, you could cancel the 2's, and you can also cancel the 454's. It doesn't matter if you do that or not. It's just a mathematical shortcut if you wanted to. What do you get on your calculator? Do you get 1573 or something like that? Okay. How many significant figures should be in your final answer? Only 2. So what is the final answer? Either 1.6 times 10 to the third or simply 1,600 pounds of sodium. And that's fine if you put that. Yes or no? Any questions over these 3? Okay, the next one, I gave you a new equation. What do you think you do there? What do we have to figure out on this problem? Well, before you even find molar masses, you have to figure out who's who. Do you agree? You've got to figure out who's who. Who is C2H4? Ethylene. So this is ethylene. Who's that? Who's this then? Ethanol. Now, I'm going to be quiet and let you try it. You have everything you need to know how to do this problem. Same exact concept. This is a balanced equation. See what you can come up with. Okay. All right, what comes next? Good, and that comes from the balanced equation, and everything's 1. Now, some people would be saying, well, don't put it then, it's just 1. Put it. Why? Because your units don't work if you don't, and you've got to get your units to work. So it's 1 mole of C2H4. What are we trying to find? So what goes on top? 1 mole of C2H5OH. That means moles of C2H4 cancel. Now what do we do with the C2H5OH? So go find the mass of it. Tell me what you got. What do you get for the mass? 46.08. So 46.08 grams per 1 mole. I'm going to do something mean. Everybody from here back, move up. Everybody from here back, move up. You don't have to take all your stuff, just take your notes. Just take your notes and move real fast. I see squinty eyes, and I see sleepers, and I see heads on faces, and I see waiting for me to write things down before you do it. So move up. Get engaged. You back row Baptist. Sophia, move up. Come on. Come down front, guys. Join the crowd down front here. Get active. Come on. No. Down front. Both of you. There's seats. Come on. Down front. Here's a seat right here. Mackenzie, move your stuff. Here's a seat. You don't have to bring all your stuff. Just move. Come on. Now wake up, people. I appreciate you coming, but if you're not here, what's the point of being here? Okay? What'd you get for your answer? 23 grams C2H5OH. All right, the next problem. The problem with the next problem is you don't know who's who in this problem. Read it, see if you can figure it out. Who's who? Who is C7H6O3? Say it one more time. I'm hearing two different things. You say acetic acid. Anybody disagree? You are correct. It's salicylic acid. Guys, all of you should have known which one was acetic acid. Acetate makes acetic acid. So which one is acetate? Where is acetic acid here? HC2H3O2. This is acetic acid. This is obviously water. Who is this? Aspirin. And this is the salicylic acid. Now somebody this morning asked a great question. They said, I thought all acids had to have AQ after them. And yes, for all of the inorganic acids that I taught you, you had to put AQ after them. This is an organic acid. Organic means has carbon, basically. I haven't taught you about organic chemistry yet, but this is still an acid. This is still an acid, okay? And I know that's confusing, but you should have recognized acetic acid. And you knew water. You should have known this was aspirin because it's being what? Produced, formed. So then that would only leave this one left over to be salicylic acid. So that you would be process of deduction. You should have figured that out. What's the given? 100 grams of salicylic acid. So 100 grams of the C7H6O3 All of this problem is exactly like what we've done. So try it. Try the problem. What do you get for the mass of salicylic acid? So where's that going to go? So 138.13 grams goes on bottom. 1 mole. Guys, bring a calculator to class, okay, please? Should be able to get the next step. What is it? Mole to mole ratio. What do you get for the mass of aspirin? 180.17. Where's that going to go? So 180.17 grams on top, 1 mole on bottom. And then what's my last step? So what goes on top? 1 kilogram on top and 10 to the third grams on the bottom. And again, that's still aspirin. How many significant digits should be in our final answer? 4. So what's the final answer? Kilograms. C9H8O4. 0.1304 kilograms, C9H8O4. Yes or no? Question on this problem. All right, the next problem is a very good compilation problem, meaning it has everything we have done math-wise in one problem. Almost everything we've done math-wise. You have dimensional analysis using what as a conversion factor that we did early? Anybody tell what special thing has to be used as a conversion factor here? Say it again. Which is called, do it the other way, and it's called what? Grams per milliliter is what? Density. Now, why did she say that you had to do density? Look what we have here. It asks for liters of water. But none of the other problems we've dealt with have dealt with volume. Am I correct? Every other problem we've dealt with has done, it's what's it talking about usually? Mass or moles, right? So what's the only way to get mass to volume? Density. What's the density of water? Okay, so you're going to have 1 gram per milliliter. What are you going to start with? 5 pounds of aspirin. You're going to convert pounds of aspirin to grams of aspirin. Grams of aspirin to I'm going to be quiet and let you ponder. You have everything you need to do this problem in front of you. You have done other problems just like this. It's stoichiometry. Guys, don't wait for me. Pick up your pencil and write. Don't wait on me to do it. What's my first thing? So 5 pounds of aspirin. 1 pound is 454 grams. Now what? Yes or no? I'm going to review a minute. Some of you had that written down and that was it. Guys, this step right here was old dimensional analysis information. This is molar mass. This is mole to mole ratio. From equation. I think it would really help some of you to write these notes down if you want to pass this class. What do you have to get moles of water to? Grams of water. How many grams are in a mole? 1 mole of water. So again, that's the molar mass. If you're confused as to how to find molar mass, it's 2 times 1.01 plus 1 times 16. Where did I get those numbers? Periodic table, okay? This morning I saw someone get a molar mass and they were multiplying everything. So I had to stop and make sure we got that fixed. So here it's 9 times 12.01, 8 times 1.01, and 4 times 16. That's where the 180.17 came from. All right, now we're back to old dimensional analysis. Because we can't do anything, we don't ask for mass this time, we ask for liters. So it's 1 gram per 1 milliliter, and this is density. Grams cancel, and then 10 to the third milliliters in 1,000, or I can't write, can I? 1 liter. 10 to the third milliliters in 1 liter. And again, all this is water. All of that is water.
Does it matter where you did your mole to mole ratio, what's on top versus the bottom?
Absolutely.
Can you explain that?
Yes.
Because
The question she asked, does it matter who's on top or bottom on the mole to mole ratio? Who are we all the way through here? Aspirin. You have to get out of aspirin.
Okay, I just got confused. So I originally had it like that, but then I switched.
You had to get that substance to cancel out.
Then you went back
And I'm now in water.
on top.
Water had to be on top.
I mean, in the next step.
Water is you're in water from then on.
Okay.
This is all water. This is all water. This is the only step that switches you from one substance to another.
Okay.
This is like an interchange that gets you from I-65 to Natural Parkway. And so you're no longer on there, you're on water now. I did not mark this out, but it's still water, water, water.
Okay.
Okay? Final answer. What did you get? Water. 0.23 liters of water. Now then, one of the things that I think this problem does a good job of is showing you a byproduct of a chemical reaction. Now, what do I mean by that? What if you had to say, this is the, fill in the blank, this is the chemical reaction that makes aspirin. That's what you would say, isn't it? You would tell me this is the reaction that makes aspirin. In fact, if you had been fortunate enough to take Mrs. Skipworth's Chemistry 109 class, and she probably wouldn't have move people up and call you out and be mean to you like I am, but if you had taken her class, you would have gotten to make aspirin. She actually, I don't know if she still does, but she used to make aspirin. She teaches at the South Campus, and she would actually have her 109 students go to lab and make aspirin because she had 25 students in one class, so it's not 75 like we do sometimes. So she would go in and make aspirin. But here's what's interesting. Is aspirin the only product that's made? No. And that's one of those weird things that we don't realize sometimes. We think of, we're making brownies in our oven. And we are making brownies in our oven. Do you know what else is given off in the process of that making brownies? There's some gases and some of it's water vapor. And it's very few times do you see this, but occasionally when you're cooking something, you may see the wetness on your door glass. Have you ever seen that? That means you made some water vapor when you were cooking whatever you were cooking. But you might have said, well, I baked bread. But you could have said, I made water. Because you did. That's what you were doing. You were making water in the process of making bread. And I wanted to point this out because this is one of those, not something you're going to think a whole lot about, but it's important for a bigger scale of things than what we're talking about chemistry right now. Factories. If you ever have an opportunity to go to a factory that makes something, which is what most factories do, but some factories only put things together. I'm talking about making something. For instance, if you go to a factory where they're making Windex, or if you go to a factory where they're making detergent, Hewish, or it's not Hewish anymore, is it Hinkle? Here they make the Sun, what is Sun for? Laundry soap and Snuggles fabric softener. They make that. I don't know which one for sure they make here, but I think they make the Sun. They may even make the Persil here, the laundry detergent. That is a neat process because they are chemically combining. Are there going to be products that are formed that aren't in the soap bottle? Yeah. Think about this, for instance. Wherever they make aspirin, I bet they're not making 5 pounds at a time. Would you probably think they're probably making more than 5 pounds? But what else are they making besides the 5 pounds of aspirin? They're making water. Now, where does that water go? You got to figure out where that water goes, don't you? You have to collect the water, clean the water, and then put it back into the water supply for that town or community. Do you follow now where I'm going with this? Gone are the days of just dumping it down in the river, hopefully. We don't want our fish to be on aspirin all the time, do we? Because there's going to be some aspirin in that water too. Do you follow what is going on now? Now, remember this because in a few minutes I'm going to use that same scenario with what goes on in your body. Okay, so keep that thought in mind. Now, let's flip to oxidation reduction. Oxidation reduction reactions are a form of chemical reaction that it's the only special one right now that we're talking about. Later on, we're going to talk about a combustion reaction, but right now we're just going to talk about oxidation reduction reaction. And first of all, before I even give you the electron point of view for oxidation reduction, I want to write in your notes the simple point of view of oxidation because people miss the obvious. If adding oxygen to another element, oxidation is happening. And I wrote that in a much longer way than I had to. I could have just said, oxidation happens when oxygen is added. Oxidation happens when oxygen is added to an element. That's one time oxidation occurs. If oxygen is added to an element and forms a compound that's now an oxide, did oxidation occur? Yes. That is sometimes an obvious that people miss. So, iron oxide, I believe it's iron 2 oxide, is commonly called rust. What does that tell you that happened to the iron? It oxidized. You follow? Okay? Don't make that part hard. Now then, what most of the time we write is oxidation is the loss of electrons. Reduction is the gain of electrons. Oxidation is the loss of electrons. Reduction is the gain of electrons. You had this, if you've had a micro class, I believe they taught you this in micro. Maybe in anatomy as well, but I'm pretty sure it was it micro? Students tell me that you learned it, so that's where I'm getting that information. All right, one of the things that I want to remind you of that should help with this, remembering which one's which. Do you remember when we were talking about making ions and we said if you add negatives you become negative? All right. Think about your status per se if you are more negative. Would you say that you're kind of reduced? Does that, you follow me? So if you gain negatives, are you reducing yourself? Yeah. That's what this is. Lose electrons, so you lose the negatives, you're oxidized. If you gain the negatives, you're reduced. A biology teacher told the students this. The students passed this on to me. Another way to remember it is Leo says grr. Now, who's Leo? The lion. Some people don't know who Leo is. Leo is the lion. Leo says grr. Okay? Now, what's Leo? Lose electrons, oxidize, gain electrons, reduce. Lose electrons, oxidize, gain electrons, reduce. The picture on the bottom of this page shows us an example, a real example of when you have oxidation and reduction going on. And I'm going to label who these things are. This is zinc metal, just like a piece of metal. So it's zinc metal. In this container, the blue liquid is copper 2 nitrate. So we have zinc metal sitting in a solution of copper 2 nitrate. Later we are going to learn, I'll tell you this now, but later we are going to learn that when copper 2 nitrate is in solution, meaning it's in water and it's dissolved, it breaks down into copper ion and nitrate ion. So basically that works for sodium chloride as well. When you take sodium chloride and you dissolve it in water, you basically now have sodium ions floating in there and chloride ions floating in there. That's what happens to ionic substances when they dissolve. They dissociate into their ions. So the reaction, there's a reaction, an oxidation-reduction reaction that's going on right now. This is the reaction. Zinc plus copper 2 nitrate yields copper plus zinc nitrate. This is an aqueous solution. This is an aqueous solution. That just means these substances are dissolved in water. This is a solid, and this is a solid. So zinc solid plus copper 2 nitrate yields copper solid plus zinc nitrate. Now what we are going to figure out is who is oxidized, who is reduced. So how do we do that? Well, zinc starts off as free metal. Isn't that what we said? This is just the metal zinc. Free elements that are not in a compound have no oxidation number, meaning it's zero. They have a zero oxidation state, meaning they're free, they haven't lost or gained. We all agree with that, right? So nothing's happened to them. Now what does zinc become on this side? Zinc nitrate, but what does that mean? It's an ion now with what charge? +2. Now some of you are like, I have no idea how she knew that. Well, first of all, what is zinc's charge over here? +2. If zinc is in a compound, it is always +2. Furthermore, what is nitrate's charge? -1. Do you have 2 nitrates? That means zinc is what charge? +2. How did zinc become +2? It lost 2 electrons, which means then zinc has been oxidized. So zinc is oxidized in this reaction because it goes from zinc solid to +2. And guys, the picture shows you this. I didn't show you the parts of the picture, but look at the picture now. Zinc strip, what's it telling you happens to zinc? This is the gray little pieces here. Zinc loses what? 2 electrons. And now you have these zinc ions floating around, and what charge do they have? That means zinc has been oxidized. Copper starts off as what? +2, but it goes to free copper element, which means it has been reduced. Copper is reduced. Now let me further explain this, because if you had a high school chemistry class, you might have gotten to do an experiment like this. If we were to do this real experiment on this piece of zinc down here that's in the solution, guess what you would see on the surface of this? Not white, you'd actually see the copper. You would see the copper. In other words, the copper metal is plated onto this strip from this reaction. So the copper comes out of this solution and lands on that zinc strip. Because copper is reduced, zinc is oxidized. Yes or no? All right, let's look at another scenario. Some of you like sentences, so here's the sentence for you. A compound that gains electrons is reduced. Do you agree with that?
Yes.
While causing another compound to be oxidized. So the compound that gains electrons while causing another compound to be oxidized is called the oxidizing agent. A compound that loses electrons is oxidized, while causing another compound to be reduced is called a reducing agent. So taking the example we just did, zinc is what? What is zinc? What's happening to zinc? Zinc is oxidized. That means zinc is the which agent? No, if zinc is oxidized, it is the reducing agent. Zinc is the reducing agent. So zinc is the reducing agent. The copper is the oxidizing agent. Now, I did not mention nitrate in any of this. Why didn't I mention nitrate? Because is nitrate -1 here? Is it -1 here? So nitrate didn't do anything. It just was out for the ride, but it didn't do anything. When considering neutral atoms, that means free elements, like we had here with zinc, metals lose electrons, and nonmetals do what? Gain. When we are considering ions, like we did here, copper +2, cations tend to do what? Gain. Look, had it already lost 2 to be +2? What did it have to do to be 0 again? Gain. That's the weird thing. That one's, you got to think about it. You got to wrap your head around that. Cations tend to gain. They've already done their losing to become positive. Now they need to gain to get back to 0. Anions tend to, because they have extra already. Good. So we're going to identify the species that is oxidized or reduced in the following example. Magnesium becomes +2. So it starts off as free and it becomes +2. How does it do that? It loses electrons. So magnesium is oxidized, which means hydrogen is reduced. Now these first 3 are very simple because there's nothing else in there. So it's one is one thing, the other's the other. Don't make that harder than it is. If one's oxidized, the other one's automatically reduced. Zinc to zinc +2. Zinc is oxidized. Hydrogen is reduced. Now here we have iodide, I-1. It goes from being -1 to neutral. What does it have to do to go from -1 to neutral? It had to gain an electron. Yes or no? No. Think about it. Does it already have an extra one? Does it have an extra electron right now? Look at iodine. What does iodide look like? Xenon? So it had to gain one, right? So in order to become free, it has to lose it. Now that's what I'm saying. You've got to get your head wrapped around. If it's already negative, then you've got to get rid of the negative to go back to free. Yes? So iodine it has to do what? It has to lose the electron. That is oxidized. Bromine goes from free to -1, which means did it add an electron? So that means it is reduced. Yes or no? In the next example, they don't have charges given, so you have to figure it out. What is silver's charge here? What's bromide's charge here? So what's silver's charge here? +1. So silver goes from +1 to no charge. It had to gain. Think about it for a minute. If it already had lost one to be +1, then doesn't it have to gain it back to become neutral? So that means silver is reduced because it has to gain. I'm going to write that for you. Must gain to get back to neutral. And I'm going to make a note. Ag plus 1 must gain to get back to neutral. Bromine starts off as -1. Yes? It becomes neutral. What does it do? It has to lose that extra when it has, right? So bromine is oxidized. Bromine is oxidized. Now I'm going to show you another equation that's not on here. Then I'll come back and do the pacemaker. But I want to show you something. There's two things I'm incorporating into this concept that I want to show you next. We mentioned the side reactions that occur. I have a little project for you to do over your break. Get a little packet of oatmeal or Cheerios. They don't have to be the expensive Cheerios, and I don't know if the Honey Nut work, but I know the regular ones work. If either way, whether it's the bag of oatmeal, the little package of oatmeal, or the Cheerios, the bag of oatmeal is already crushed, but the Cheerios, if you get the Cheerios, crush them on a paper plate. So just take a cup or something and just crush them up on a paper plate. Take a magnet underneath the paper plate and just start running it around on the bottom of the paper plate, whether it's the oatmeal up on top or the Cheerios, it doesn't matter. And after just a little bit, you're going to start to see something running around with that magnet. Anybody know what it is you're seeing? Say it. Iron. You're going to see iron. Now, what kind of iron is that? Is that the same kind of iron that a magnet sticks to? What kind of iron does a magnet stick to? Iron metal? Yes? So you're telling me that iron metal's in my Cheerios? Iron metal's in my oatmeal? Yes, that's exactly what I'm telling you. Now, take it a little step further and read the box occasionally. Guess what the box says? Does anybody know exactly how the iron is listed on the box? Reduced iron. You didn't know there was anything about oxidation reduction on your cereal box. But it probably says in the ingredients, reduced iron. Now, what would reduced iron be? Iron metal. Now let's look at what you just did right here. Iron, but this isn't iron, but pretend it's iron because it's the same kind of thing. It's a metal, right? In this situation, silver is a compound, in a compound. What does it do? Gets reduced. When it's reduced, is it in its free metal state? That's what that reduced iron is. Well, now you're thinking, well, how can I eat that and do any good? Because what's in your stomach? I want to know who. So this is your iron solid that you're putting in your stomach. This is what's in your stomach, hydrochloric acid. Guess what you're making? Now, I'm not sure if it's iron 2 or iron 3. I'm just going to call it iron 2 for simplicity's sake. And hydrogen gas. And to balance this, I'll put a 2 there. And this is still in the aqueous solution in your stomach. What you've just done is you've made iron ion now in your stomach. You started off with iron metal that would stick to a magnet. I guess that means if you eat enough, you can just take a magnet and, no it doesn't. No it doesn't. Why not? Because once it hits your stomach, what's it made now? Iron 2 chloride. So it's iron ion. Now, before I talk about the side reaction taking place, let's figure out. Iron is what in this reaction? It goes from neutral to what charge? +2. That means iron is oxidized. Now, who else is having anything happen to it? Hydrogen is. Good job. Chlorine is chloride here, -1, and it's chloride here, -1. So nothing happened to the chloride. But hydrogen is what? Reduced. So iron is oxidized, hydrogen is reduced. Now then, let's talk about the side reaction that is occurring as you are eating your Cheerios and oxidizing your iron. You're reducing hydrogen, and what did I put after this hydrogen? Burp. Now do you know why you burp? Think about all the food that you eat. Now think about all the side reactions that are happening. Is there a lot of gas produced? Yes. Now you know why you have so much gas. That's why. That's why. And that's why you'll burp like that. And it could be a big burp, could be a little burp. And you realize, that's why, drinks, cold, soft drinks. Is there a lot of gas going on in there? Yeah, man, we can really go to town then. So, does that make sense? All right, the last thing, pacemaker. This is a lithium iodide battery pacemaker. Now, I don't know if all pacemakers have a lithium iodide battery. My mom has a pacemaker, and I don't know. I should ask. She won't know, I don't think, but I should ask the doctor what her pacemaker battery is. I don't know. Another book had mentioned that it was a lithium iodide. Most of your battery reactions, like your computer laptop battery, any rechargeable battery, that is an oxidation reduction reaction going on in there. Your car battery, that's an oxidation reduction going on in that battery. So lithium in this particular reaction is being what? Lithium goes from free lithium to +1. That means it's what? Oxidized. That means the iodine is reduced. Okay? So it's happening all around us. And honestly, the food, I think that's probably one of the neater places to think of it. Okay? All right, I am going to stop there, but I would like for you to stick around if you have not seen your test.